Okay, good evening, everyone. I'm sorry, I'm laughing because there's a bird in our house, so everyone's like yelling. So if you hear any noise in the background, that would be why. Um, Before we begin, does anyone have any questions regarding Chapter 3 randomization? Because today we will be moving on to Chapter 4, instrument variables. So if you have any doubts, I would recommend asking now so we can fully move on. Okay, great. So we're gonna start on IVs today, and it's another type of methodology to look at impact evaluations. So I'm going to share my screen. Okay. So we're going to talk about instrument variables today and over the next week probably. Um, have any of you guys used instrument variables before, or maybe learned about them in an old econometrics class? Or is this fully new to some people? Yes, we've seen them before. Okay, awesome. Um, so it's a really cool methodology because it's basically a method most of the time used in retrospective analysis. And we talked about retrospective analysis before in chapter 2, or maybe chapter 1. And basically the problem is when you're looking data from the past, you might not necessarily have that baseline data like we had in randomization. So with that baseline data, as you guys did in your assignment 1, you can easily check that there is an absence of selection bias by looking at covariates between the treatment group and control group. So you know exactly who's being treated and what all of their characteristics were even before they received treatment. However, in some cases with retrospective analysis, it's hard to precisely pin down a treatment point. um, Maybe one group's always treated and one group's never treated. There's a lot of things different. You might not always have specific data on the treated group before they're treated. So a lot of things make retrospective analysis a lot harder. And so instrument variables are really a method to address this problem. Okay, so yeah. I mean, we talked about randomization and it's super easy, super straightforward, but it's not always practical in the real world because Um, basically, with an experimentation, we have the power to assign individuals into treatment and control groups. However, in many cases, there are going to be programs that already exist, and people will have self-selected into these programs, um, or decide not to participate, right? So there is self-selection bias going on here, and we need to address that to get a causal estimate. Because maybe this some program was implemented and it wasn't implemented using randomization. That doesn't mean we don't care about the effect of this program afterwards. Maybe we still want to learn something about it. There just wasn't enough planning to make an experiment at the time. So we should always be able to go back and look at a program even if we don't have prospective analysis. And therefore we need tools to do that. So the next the rest of our models will be using retrospective, right? So randomization experiment is our only prospective methodology in this class. So from here, we're going to be looking at IVs, diff and diff, synthetic design, matching, hopefully we'll cover, um, regression discontinuity design. So these are all methods that can definitely be implemented retrospectively. So this is a lot more realistic because I guarantee none of you are doing a prospective analysis for your thesis. It's a lot harder to have that data because you actually have to go out and create it. Whereas retrospective data is more common because it's using data that already exists to try and answer really important questions. So it's a lot cheaper and obviously more relevant to us as researchers because we don't have money to go and make experiments. So we're going to use data that already exists. And with that, you guys are going to need different tools to assess your question. Okay. So yeah, instrument variables is one of these techniques, and it's trying to get around selection bias, the harsh truth. So basically, it's solving the problem of omitted variable bias, right? So if we're just running a regression, if we care about going to the effect of going to the hospital on our health outcome, and we can't randomly assign who goes to the hospital and who doesn't, we need to figure out what the omitted variables are so that we can address that problem. Or if not, we can use an instrument variable approach and try find some exogenous window which creates people to go to the hospital that's not going to be correlated to our outcome. So we'll talk about that more obviously, but this is just one method to try and address the problem of selection bias and omitted variable bias, which are essentially the same. Okay, so let's just consider this common omitted variable bias problem. So suppose we are interested in measuring the effect that education has on wages. So let's say education is measured in years of school and wages in dollars. So our standard regression, our OLS regression, would be that our wages is a function of our education, right? So yi is our outcome variable, wages, equals to alpha plus beta SI, where SI is the years of school or years of education for individual I, and eta I is our error term. Okay, so what do you guys think could be an omitted variable in this regression? What are we missing that could explain wages?
It can be.
Jorge, right off the bat, said ability. That's very true. Ability would definitely be the unobservable variable. And then Nicholas says initial socioeconomic status. That's true. If you come from a richer family, you're probably going to get more years of education, and maybe they know people that will get you into a better job too. So that's kind of affecting years of education and your outcome variable. Age, yeah. So of course, the older you are, you probably have more education and also more experience, which can get you a higher wage. So normally people that are older earn a higher wage just because they have so much more experience in the labor force. And also, yeah, experience it. So the big one is that we can control for what Nicholas said, socioeconomic status, and we can control for what Susanna said, age, but we cannot control for ability, right? Because ability is unobservable. So how can we quantify what ability is when we can't see it, right? Because it's probably the case that people with higher ability are able to obtain more years of education, and they're also able to go out into the labor force and earn a higher wage just because they're more productive. So it might not just be that education is increasing your wage, it's that more people with higher abilities are getting more education and also receiving a higher wage. So that's not the causal effect of education on wage, it's actually just this omitted variable bias in our estimate, right? So if we don't control for ability in our regression, will our beta on years of education be overestimated or underestimated? Let me ask that again. Okay, so if we have ability as our omitted variable, will our beta on the effective education on the wage, will that estimate be overstated or understated? Overstated, yes, because because basically ability has a positive effect on wage. So when ability is not included in our regression, we have that positive effect contained in our beta. So our beta estimate is bigger than it should be, so it's overstated. Does that make sense? Or is that confusing? Right? Because if you controlled for ability in your regression, say we were able to put ability in, then ability would have a positive effect on our outcome wage, and therefore the effect of education would be lower. That's why when we don't include it, the effect of beta is higher or overstated. Great, then. Very good. Smart thinkers today. So yeah. So obviously there are other omitted variables, but the one that is unobservable is ability. And this is because people with higher levels of ability are likely to not only obtain more education, but also be able to earn higher wages just because they can work more efficiently and be more productive. So then, obviously, if we have omitted variable bias, we aren't obtaining a true causal effect because, as we said, our estimate of beta, so our estimated effect of education on wages is higher than it actually is in reality. So therefore, we're overestimating, and that means we don't have causality. So maybe education has zero effect. It's just ability causing more education and higher wages. That would be the extreme tail. Whereas maybe there's some combination of education and ability that affect your wages. But we need to figure out what the effect of is of ability on our outcome variable to be able to know, or we need to find some sort of instrument variable so we only can find the effect of education on wages, right? We want that ability estimate removed from our education variable. So how can we separate the internalized effect of ability from education? Because we only are interested in the effect of education, an extra year of education, on our wage. But if ability affects how many years of education you get, that's not a clean variable. So we need to find an exogenous way to look at education on our outcome. And so that's really the motivation of an IV, is to somehow find a clean channel between our X variable of interest and our Y variable of interest that removes other unobservable or omitted variables from our estimate of beta. Right? So if you think about the error term again, so since ability is not controlled for in the above equation, because it's not easy to control for because we can't observe it, unobservable, so then it will be contained in our error term. So eta, I, will be a function of AI plus VI, where AI is individual ability, so that's our ability term, and then VI is the random component of the error, so that's just pure noise. And that's the only thing we want to be in our error term, right? We just want pure noise. Because if there's something systematic in our error term, like ability, that's omitted variable bias by definition. Okay. Does that make sense? Why ability would be an omitted variable bias and it would overstate our effect of beta, so of education, when we don't control for it. But we can't control for it. We would if we could, but we can't. So we don't. So we need another method to address it. Okay. So assume that the only reason that SI, which is the years of education for individual I, and eta I are correlated is because of the ability component in the error term AI. So we're saying basically if we removed AI from the error term, we're only left with the VI, remember, because we have eta I is a function of AI plus VI. This is ability, this is just white noise. So if we only look at the relationship between SI and VI, we have 0 because they're completely independent. There's no co-movement between the two. So that's what we want. However, there is correlation between SI and eta I, and that comes strictly from ability, right? Because ability is in our error term, we're not controlling for it, and it affects our years of education. Okay, so that we have the expected value SIVI equals 0 tells us that there is no co-movement between the noise term, our VI, and our independent variable of interest, which is SI. And that's clear when I say independent variable, I'm talking about X, and dependent variable, I'm talking about Y, because I will typically refer to them as dependent and independent, or X and Y. Yeah, that's about it. The regressor would be X. Okay. So, of course, since ability is causing all the problems, but it's causing the bias in our estimation, we would like to control for it. We would like to remove it from our error term. So if we could, we would put it into our regression of wages on schooling, or the effect of going to school on wage, and that would give us a regression written as here in equation 3. So yi, wage, is a function of alpha plus beta si, education, plus gamma AI, so ability. And then you see how the error term is transformed to just VI. And what is VI? It's just noise. So that means we have removed the selection bias because our error term is just white noise. There's no bias in it. So we would like to control for ability, but of course it's unobserved and we cannot put it into our regression. But it would be our causal effect of interest in this case. So if the only correlation, as we said, between SI and eta I, our original error term, is ability, then when we control for ability, we have causality. But of course, as Nicholas and Susanna said, there's other things that obviously affect wage, such as age and income, so those would be included too. But this is just a very simple example. So we're just thinking of ability because that's the hardest one, because we can't control for it, right? We can control for the other two because they are observable. Okay, is that clear, everyone? Or is there some confusion on the error term? Clear. Thank you, Jorge. I had a meeting with Sandro and Fernando and all of the professors of the econ department, and they told me that maybe I'm talking too fast and there's some concerns about having a class in English. So I really want to support you guys if you feel like you're struggling with the English class. I know it can be hard when you're used to hearing Spanish all day and then to suddenly hear English. It's really kind of hard to switch that. So I'm completely happy to go over anything again. And if you're concerned about submitting assignments in English, just come talk to me. I don't expect the grammar to be perfect or anything, just as long as you can communicate your thoughts and you feel like I am explaining things well enough, then we're fine. So, but do talk to me if you have concerns, because I don't want anyone to feel confused or left behind. because I speak Spanish, but trust me, your guys' English is better than my Spanish, so it'd be better for all of us in English, I guarantee. You guys could teach me a class if it was in Spanish, I'm confident. So anyways, so right, our ultimate goal is to conduct an impact evaluation of schooling on wages is to estimate beta, right? So beta is the effect of schooling on wages, which is causal because it is in the absence of any omitted variable bias. So that's our goal, obviously causality. When is our goal not causality? Never. Okay, so now some assumptions and estimates. So let us define our instrument variable as Zi. So Zi will be our instrument variable. And the instrument variable can be used if researchers have access to a variable that is correlated to the causal variable of interest, SI, and uncorrelated to the error term, or any other variable that affects the dependent variable, wage. Okay, so the first restriction, the correlated to the variable of interest, XI, is written as the covariance of SI, ZI is not equal to 0, right? So we're saying that there is a relationship there. There's co-movement between SI and ZI. And that's referred to as the relevance restriction, because if there was no relationship between our instrument variable and, let's say, education, if they don't move together at all, how are we going to explain education from our instrument variable? So we need them to be connected so that it's relevant. And so we need that variation to move together so that we can use whatever variation is the same between X and Z to explain our outcome variable. So it's really important that you have relevant instrument. And also the second one can be written as the covariance of A to I, Zi is equal to 0. And that's referred to as the exclusion restriction. So this is about the selection bias problem, because if we didn't have this condition, it would be no different from using education on our outcome as this instrument variable, because they're both related to ability somehow, or whatever variable is omitted. So we really need this variable, whatever it is, as an instrument to be unrelated to other variables that might affect our outcome. So we'll talk about some examples of that, but a common, let's see, for education, a common variable that authors used to use, which will, I think there's a paper that I talk about later, is distance from a university. Okay, so your variable is distance from university, and basically the authors think that distance from a university should be able to explain how many years of education you get, because if you live closer to a university or school, maybe you'll get more years of education than people that live further away, because it's just easier to go to school, and so the cost of doing so is lower. However, distance from university should be kind of random to ability, because people just live where they live. People that are getting educated are normally teenagers, and their parents decide where to live. So there really shouldn't be a relationship between ability and the outcome variable, wage. So for that reason, they argue that the relevance restriction is satisfied, because we have that being closer to a university gives you more years of education, so that's relevant. And then the exclusion restriction would be that distance to university isn't related to ability, right? So then that would be satisfied. However, there's been critiques that this isn't actually a good IV anymore, because obviously distance to university. We all know that places really close to university are more expensive. And so maybe only richer families live close to university. And as Nicholas said, income could be affecting both the education and the wage. So then that would not be a valid IB because then it would break the exclusion restriction, right? So it is really hard to come up with an instrument variable that satisfies both restrictions 1 and 2. I'm sure you guys have all tried to think of some for your thesis, and if you've thought of any good ones, let me know because I love to hear them. I've never thought of a good IV for any of my own research because it's the hardest thing in the world to meet both the exclusion and the relevance. But in like theoretically, it's really solid technique to find causality and remove selection bias, and it's fairly testable, which makes it like a pretty strong instrument or strong methodology. So there are some really strong IB papers out there, but just due to the difficulty of finding an instrument variable, there's just not so many papers. Okay, so then we write beta based on the relationship between our outcome variable and our instrument, and rescale it by our independent variable and our instrument. So beta is equal to the covariance between yi, so wage, and zi, and then divided by the covariance of si and zi. And then if you want to make it look like a neat, basically this will look like the Wald regression, which I'll talk about later. So you can just divide each side by the variance of zi, and this is the regression coefficients actually, so then it looks like just covariance yi zi divided by the variance of zi, and then divided by covariance si comma zi divided by variance of zi. So it's interesting because beta is the ratio of the population regressions, right? So these are two population regressions of yi on zi, right, up here. This is the regression of yi on zi, which would be the first, or the reduced form. And then the bottom would be the regression of si on zi, and that's called the first stage, okay? So the first stage is always our instrument variable on our independent variable, and our reduced form is always our instrument variable on our outcome variable. I'll write that down. Actually, I might not do that. Draw. Oh, I don't like that. Hey. yi is the front. Oh, I won't be able to do alpha. Come on. Here we go. So alpha plus, we'll just call it beta. We always call it beta. So, not yi. Nice. I'm sorry, you guys. Just so much pressure. Okay. So si beta zi plus one I. Okay, so this is our education, or I could have called it X because that's more straightforward, but oh god, hard. and then this is our IV. We could say in this case, let's just call it, this is education and this is distance from university. And then our reduced form is, oh, okay. I have a question. In the selection bias problem, we observe seeing the error. If it's white noise, there's not. Okay, yeah, so in the error term, if it's pure white noise, there's no selection bias, right? Because we have an omitted variable bias problem when there's some omitted variable in our error term. So if we see that our error term is complete white noise, then obviously there's no omitted variable bias. I mean, we can't really see the error though, so it's more of a theoretical argument, but yes, correct. Okay. So reduced form is always our instrument variable on our outcome of interest. So obviously we're not really interested in education. Well, I mean, we're interested on the effect of education on wage. But to get that, we need to know how Zi affects education, and then how Zi affects wage, and then we rescale the beta. Okay, I'll just show you. I'm sorry. But yeah, we rescale the two betas to each other. So beta 1, Zi. So this is our first stage and this is our reduced form. You can see how our two variables of interest, education and wage, they're always on the left-hand side. They're always a dependent variable here, right? And they're always a function of our instrument. Because we only care about the variation in Z that affects education, and we'll take that variation and look at the effect on our outcome variable, because we suppose that this satisfies the exclusion and the, what's going to call it, relevance. Okay, so we need our Z to satisfy, oh, look at this. Woohoo, that was cool. We need Z to satisfy the exclusion restriction and relevance restriction to be a valid IV. So when we have that, we know that our Zi is some sort of exogenous variation that has no omitted variable bias problem that is going to affect education. And so we only care about the relationship between Zi and Si, or the covariance, because we don't necessarily care about the effect of Zi on Yi. We care about our education on Yi. So we only want the co-movement between Zi and Si that is the same to affect our Yi, and that will be our channel of interest. Does that make sense? Or was that really confusing? I think it's clear. So just basically, we want to measure the effect of education on wage, but when we do that, we have a selection bias problem. So we found this variable Zi that is related to education, but it doesn't have the same selection bias problem. There's no other variable that affects our Zi that is also affecting Yi. So it's a really clean variable. It has no omitted variable bias problem. So therefore, since it's related to education, we only care about the variation between the two that's similar, or they have co-movement, and we'll use that variation to explain our outcome variable. The rest of the variation in Zi doesn't matter because it's not telling us anything about education. right? We inherently care about the effect of education on wage. We don't care about distance to college for anything other than what it says about education. Can Zi be related to another independent variable? No, it should only be related to the channel of interest, which is education, right? So it should only have an effect on our xi to be valid. Good question. Okay, I'm gonna delete this unless you guys want me to keep it. I don't think you would. I'll take the silence as a delete. Wait, new share actually. Okay. So yeah, you can see how then we're rescaling. This is our reduced form. So this is our beta of the yi is a function of alpha plus beta zi plus ei. That's our beta here. And then this down here is our beta for si equals alpha plus beta zi plus ei. So you can see how these are the betas for the two, the reduced form and the first stage, right? So the first stage is how zi affects our xi, or our independent variable, and then the reduced form is zi on yi. So then just to find the causal effect, we need to divide our reduced form, the relationship between zi and yi, and we need to say that we need to divide it by the effect of zi and si because we're only interested in the co-movement between si and zi to explain our yi. Okay, so that's the reason for that. We also need a really strong first stage, right? We need a strong co-movement between our zi and si, or our x variable and our z variable. And that's because if we have a really small relationship, we're going to find it's going to be hard to estimate a precise effect of education on wage. Right? Because if you have on the bottom hand side, so if you have on the denominator a number really close to 0, you're going to have a large confidence interval of where the true effect could lie. And so I think Vadim Marmer is going to come to you guys and talk a bit more about weak first stages, but they're really not good for an IB because they're not going to be informative. So therefore, if we want to find causal estimate, which is beta, first the instrument Zi must have a strong relationship with Si. And so yeah, that relationship between Zi and Si is called the first stage. And then secondly, the only reason that Zi should be related to Yi is through the first stage regression, right? So if Zi is related to our outcome variable through any other channel besides education, then that's a bias in our estimate. For the same reason that education estimate was biased to begin with. When we don't control for an effect of another variable, then it's contained in our beta. And we only want beta to tell us the effect of education on wages. So if there's any other relationship between Zi and Yi, then that's containing other effects that we don't want to contain, right? So that's really the reason why we need this kind of singular channel from Zi to Yi through our X. And that's what makes it so hard to find a valid instrument, is because we can think of a million instruments that satisfy relevance, but to satisfy exclusion and relevance is just insanely hard. So if you guys are good at thinking of instruments, you should just do that full time and pay research, or researchers will pay you millions. I mean, researchers are poor, but They'll pay you something. Okay. Questions so far? Okay. Let's take our break now, just because. I'll see you guys in 10 minutes. Okay, so one question first. In the case that our instrument is weak, is it recommended to use it? No. And that's just because it's not going to give you an informative estimate. So if you have a really weak relationship, there's not much explanatory power of Z on X. And so that won't tell us much about our outcome variable either. So it's really not that informative for a larger population, and the effect might be really dependent on what sort of instrument you use or what kind of variation is contained. So it's really not recommendable. Okay, take a break. I'll see you at 6:57. Oh. Okay, hello everyone. Let's start again. Every time. Okay, where was I? Okay, yeah, so just to refresh, we were just talking about that the instrument variable should only be related to our outcome variable through the first stage regression, so through our x variable. And that's because if it's related to our outcome variable through any other variable in addition to our x variable, that is by definition omitted variable bias. So we do not want that, and that would mean that our instrument variable is not valid. Okay, and so we also do not want a weak first stage where the relationship between our z and our x is really small. If there's barely any co-movement, there's not much of z to explain x, and so we only take that co-movement between the two to explain our y. So if there's very little to explain y, we're likely not going to have enough variation to make any meaningful analysis. Okay, so often papers aren't accepted that have weak IVs. You can do a weak IV test, and that should determine whether or not you should use an IV. Okay. Okay, so yeah, this is basically what I just wrote on the whiteboard earlier. These two regressions will be our first stage and the reduced form. Don't be scared off, I just used different coefficients, but let's say our first stage is always, wait, what? Oh, okay, that's weird. Wait, what's x? Captures the z on y. I really don't know why I put x in there. What was I doing? Oh, that's our alpha. Okay, well, okay, no, I know where I am. Okay, so just call x random covariates. Also it could be our constant term and coefficients, all that, or covariates. And then, so we really care about the relationship between zi and on si, which is our first stage, and our reduced form would be zi on yi. Okay, so you can see how we have the coefficients pi 1, 1 for our first stage and pi 2, 1 for our second. So then to capture the effect of interest, our beta will just be pi 2, 1 divided by pi 1, 1. So it's these two. That's our two betas from the first stage and the reduced form. So it's just beta is pi 2, 1 divided by pi 1, 1, which is equal also to this, right? Because these are our two regression coefficients, which is the covariance between yi zi divided by variance zi and divided by the covariance si zi divided by variance zi. Because those are our betas from our reduced form and our first stage. Is that clear how those two are the same? This is just the formula for beta broken out into each regression. So this would be what our beta estimates for our reduced form and our first stage, which is what we write here. These are just the same, like beta 1, beta 2. So this is our coefficient for our reduced form regression divided by our beta for our first stage regression. Okay. And that's saying you are only taking the variation that's left between our z and our x, or s. Okay, so now we're going to talk about inference. So basically, just some examples with respect to policy impact evaluations. Instrument variables are very useful when there is incomplete compliance for treatment. Okay, so do you guys know what incomplete compliance is? That's a mouthful. Who can tell me incomplete compliance? Not really. Okay, I'll talk about it. So remember how in randomization we said these people are receiving treatment and these people are not receiving treatment, so they're in the control. That guarantees that everyone we say that should be getting treated is actually receiving treatment, and everyone not in the treatment group, in the control group, are not. However, so before in our assignment, we basically assume that everyone receives treatment and everyone who is not supposed to doesn't. So that is called full compliance. I'll write that all. Write that in the chat. So full compliance is when everyone who is supposed to be treated receives treatment. And then everyone in the control does not. So remember how DI, our DI variable, was treatment assignment? So we can say, okay, well, you should be treated and you shouldn't. That's their assignment. But that doesn't mean their treatment status actually matches where they should be. So sometimes there's people that are supposed to be treated, and for some reason they decide not to take it for whatever reason. And maybe some people in the control somehow do receive treatment. Okay, so then we don't have perfect randomization. We have generated selection bias in our experiment now because after the fact, after randomization, some people do receive treatment that aren't supposed to, and vice versa. So that creates selection bias because people are choosing afterwards to treat or not to treat. Okay, so that's when we can use an IV actually and try and use the IV of just the initial randomization because that's the exogenous part on our outcome. So we'll talk about that more a bit later. So the nice thing is when we do have full compliance, when we assume that it's there, we just estimate the causal effect of treatment as the average treatment effect for the population, right? Because we say this is the average outcome of our treatment group, this is the average outcome of the control group. Therefore, the difference between the two groups is our average treatment effect. But when we use an IV, we can't really, like this, we can't really say it's the average treatment effect for the whole population, because then we can only look at a specific population that complied with randomization, and that those people might not be representative of the larger population, right? Because there's some self-selection going on there. So we can't necessarily say it's the average treatment effect anymore because they're not a random sampling of the full population. So yeah, in reality, programs typically offer the opportunity for treatment to a given eligible subpopulation, and some individuals do choose to participate and others choose not to participate. And in the case where there is not full compliance, so people that are given a certain assignment and some people don't comply to that, the impact evaluation can either estimate the effect of simply offering the program, right? Because the offering is still random. Like we can say, oh, well, if we offer the treatment, what is the effect on our outcome? But that might not be the effect we're interested in because just offering the program doesn't ensure that they're receiving it. And as a policy perspective, we want to know the effect of the program. We don't care if they got offered it and didn't receive it. We care if they had the program and how it affected their outcome. So it's not really desirable from a policy perspective. So then we need to find a way to measure the effect of participating in the program, which we can't do through a normal OLS anymore. That's because there's selection bias. So then we turn to an IV typically. Okay. I'm going to pause on that because this is kind of random, but it's a good example of an IV. So this is just an example of an instrument variable to estimate a causal impact. So these two authors, Kearney and Levine, were interested in the effects of watching Sesame Street. Did you guys, I don't know if you guys watched Sesame Street as children, if it was available in Spanish, but I was super in love with this show. It was awesome and very educational. So it's a really common kids television show in the United States and Canada. I'm not sure about Peru. Oh, nice. So yeah, it was in Spanish. So maybe you guys watched it too, or maybe I'm just too old. And they wanted to see how that. It's a classic. Okay, good. I'm not that old. The authors were interested in the effect of watching Sesame Street as a child on how ready children were to enter school and advance through grades. So they called this school readiness, and that just basically meant how prepared they were and how able they were to learn these new skills in school. Okay, so obviously, if we're interested in the effect of watching Sesame Street on school readiness, I think they're basically just talking about, like, I don't know, like smartness also. It's kind of just like ability to learn, I guess. So what would be the endogeneity problem here? What do you guys think? What would be the bias if we estimate watching Sesame Street on your school readiness when you get to kindergarten or grade 1? You have a TV. Yeah, you have a TV. Also, maybe, okay, so that, yeah, TV could be an indicator of income. So maybe richer parents are better able to prepare their children. Also, if parents care enough to make their child watch Sesame Street to get ready for school, maybe they care enough to do other things as well. Maybe they're more likely to make them read at night or practice their alphabet or other factors that might affect their educational outcomes besides just Sesame Street, right? So families that make their kids watch Sesame Street are probably different than parents that don't. And it could be through income, it could be through motivation for their children, or even parents' education. Maybe parents who are more educated care more about their child's education, and so they make their kids watch Sesame Street. So it could be all of these other factors other than just watching Sesame Street that are affecting how ready a kid is for school. And of course, when you're estimating that effect, we never want selection bias because then we're just measuring differences between two populations. We're not estimating a treatment effect. So how do they get around this? Maybe with an IV. Okay, so yeah, like I said, this could mean that these parents could also be more ready or likely to read to their kids or impose higher standards in some way. They could be more strict, stuff like that. Even like if they make them try harder in school, that could also make them appear more ready just because they're putting more effort in. Okay, so that's selection bias, and that will damage our causality. And so the authors address that with an instrument variable impact evaluation strategy. So this is largely because the authors were using a retrospective analysis, right? They obviously, this question about Sesame Street and education, they already had data because Sesame Street has existed for a long time, so they're going back and using older data. And that meant they didn't really have sufficient baseline information, and so they couldn't control for confounding covariates sufficiently. Okay, when I say covariate, confounding just means that it's basically, I say it's like confounded in our estimate of beta, which is we just want the effect of beta on our outcome. but there's other omitted variables confounding our estimate. That means it's just included in our estimate that we need to get rid of. I don't know if that's clear or not. I use my hands a lot. Okay. So what the authors do is they manipulate basically the fact, or I'll just explain it. So whatever year that Sesame Street was implemented in, the show was only available to certain households based on a certain radio channel, and they use that variation to measure the effect on education outcomes. So in the first few years of broadcasting, the show was not available to all households. It was only given to households that had access to this ultra high frequency, or UHF channel. Okay, so that was like a special channel, and only 2/3 of the US population lived in an area where the show was accessible because it was only accessible to these high frequency channels. So the researchers argue that since television towers were built in locations chosen by the government, even before Sesame Street was ever showed on television, this variable would, oh wait, well the variable is, so they're going to use distance from this TV tower. So they're going to use distance from tower to see how Sesame Street affects kids. So they're saying that these television towers were decided by the government even before Sesame Street was started. And so this instrument variable, distance from the tower, wouldn't be related to household characteristics or changes in the outcome. So it would satisfy, obviously, relevance because being closer to the towers meant you could watch Sesame Street. And they're saying it's exogenous because since the towers were built before Sesame Street was put on, it shouldn't be related to the outcome variable of like school readiness, right? So that's what they're using. They're using household distance to the closest television tower that transmitted this UHF frequency, and that will be their instrument. So what do you guys think of this? Do you think that it satisfies both exclusion and relevance, what do we call it, assumptions? Well, let's start off with relevance. Do you guys think yes or no it satisfies the relevance assumption? And just tell me why. Let's hear some new voices. All right, let's hear some old voices. Who thinks that the relevance assumption is satisfied by the IV distance to this special tower that transmits Sesame Street? Is that relevant?
Yeah, I think it's probably satisfying that restriction because I mean you're very likely to watch Sesame
Come on, you
Street.
guys, I believe in you.
Do you hear me?
Okay, relevance assumption is when our instrument variable is related to our x variable. So our instrument is distance to, Nicholas wanted to say something. I can't hear you. Oh. I'm confused. Nicholas, if you were talking, say it again. I couldn't hear. Oh.
Yeah, I think you cannot hear me.
Yeah, I can hear you now.
Oh, okay. Yeah. So I was saying that, yeah, relevance restriction can be satisfied because maybe people that are closer to these kind of, uh, I don't know, what are those like
Like
these
towers.
things? Yeah, these towers. So they're more likely to watch Sesame Street. So maybe, yeah, this correlation is positive. But I have a question.
Yeah.
But I mean, it can be also instrument from other channel, not only Sesame Street. So how do they attribute exactly the effect to Sesame Street?
That's true. I think that they use the fact that Sesame Street is broadcasted in a certain year, and other channels weren't broadcasted in the same, or other TV shows weren't. So they're only looking at the specific year in which Sesame Street is broadcast. So they assume that actually that's true because then these UHF people will still have access to those other channels at the same time. So they're comparing people that have access to the tower to people that don't. So there could be other television shows, but their argument is that, I mean, for young kids getting ready for school, Sesame Street was pretty much it in terms of educational material on television. I mean, this was like the 1960s, so it's not like today where there's a million cartoon shows that kids can watch and learn. This was pretty much the only one, so that would be the reason. But speaking of that, that was questioning the exclusion restriction, which I don't think it's totally okay. Yeah, so you guys are commenting on the exclusion restriction right now. So that is when our instrument variable Zi is not correlated at all to our error term, or in other words, other variables that might affect our outcome. So, like Nicholas said, maybe there's other TV shows that could also be affecting the outcome. And then Jorge says, I don't think it's totally exogenous. Exogenous places, it's not exogenous where the towers will build. I agree because I agree with both actually, but especially where the towers were built is a good answer because like these governments are making decisions where to put the towers. Obviously, they're not going to go, oh, let's just put the towers randomly. Like they're going to look, okay, where are the richest communities that are more likely to access cable television? Where are the most populated dense areas? All of these factors are going to affect where the government puts in these towers. Um, so of course, it's not really random. It's going to be a function of characteristics and demographics. And so if it's more rich areas and more populated dense areas, that's obviously going to affect education in other ways. Nicholas says, I'm not sure, honestly. I mean, being able to watch something is not the same as wanting to see something. So you don't think that there would be effect of Sesame Street on education readiness because you don't absorb the information unless you want to. So if it's coming from the parents and not the kid, then it won't make a difference. That could be true. That's more a question of whether there should be an effect or not. Okay, and then Nikos also says urban versus rural, right? So there's probably going to be more towers in urban areas compared to rural. And so if we're looking at the whole country, then we're comparing households in urban areas to households in rural areas. And that might have differences in characteristics on whatever parents prioritize more for their children, whether there's better resources in a city than an urban rural area. I don't know. The show was that easy. Yeah, Sesame Street. I mean, by the end, it's like became pretty free. I think it's like available on free channels, but at the beginning, yeah, it was pretty exclusive, I guess. Okay, Nicholas, the distance is useful as a metric for distance. I meant the distance. Oh,
Can you hear me? No.
yeah. Go ahead.
What I meant was that they use distance, and they argue that if they were close to the tower, then they must have watched the program. What I'm trying to say is that not necessarily. Just because I can watch a program because I physically can, doesn't mean that the
Oh,
family will choose to watch it.
I see. Right. That's true too. I mean, that's the thing, like, that doesn't, just because they're close to the chat tower, doesn't mean they're necessarily watching the show. But they do have this data on what households use Sesame Street for their children. So they're just using the co-movement. Actually, no, that doesn't make sense. You're right. Because you have to, no, yeah, that makes sense. So you can only watch the show if you're close to a tower, but they're using this distance from the tower as an instrument. But yeah, you're right. There's some self-selection bias in there too, because then it's like people that care more are selecting into watching, and that will affect, I guess, yeah. So I don't like, I just think it's unanimous that this instrument variable does not satisfy the exclusion restriction. The channel proposed is questionable. Okay. Yeah, so we all agree that this instrument variable is not the strongest on the basis of the exclusion restriction, because we all agree that there might be some relationship between being closer to the channel or being closer to the tower and watching Sesame Street, right? Because you only have access to it if you're within a certain range to the tower. But on the other hand, being close to the tower might be a function of income, population. If you have a bigger population, there's probably more schools around. And when there's more schools around, they have to be more competitive with each other. So that normally means the quality is higher. So maybe these kids closer to the towers have better schools than people that live in a super sparse area with very little schools, and that makes them lower quality. So there's a lot of things that could affect the outcome that are not controlled for with this instrument variable. So it's definitely not the strongest. My parents are partying without me. Okay. So yeah, we talked about this, the relevance restriction and the exclusion restriction, and whether or not they are satisfied. So of course, when we talked about the relevance, the distance to the closest television tower will determine what houses watch Sesame Street and which do not. We all agreed that that should have some relationship, just based on the fact that if you're far away, you don't have any access. So even if it's a small population that will watch Sesame Street, there is a distance relationship there. And then the exclusion restriction says that distance to television towers should not affect the outcome of interest, which is school readiness, by any other factor besides through watching Sesame Street. And we all agree that other things could be affected or be explained by that distance variable. Okay. So yeah, I said what they found, I guess. So they found that areas where there was high UHF television reception, so people that were close to the tower when the show began, children were more likely to advance through primary school at the appropriate age. So I don't know if we feel comfortable that that's causal, because that could be through a various amount of other factors, such as like income, like parents that make their kids watch Sesame Street more, etc., etc. So yeah. What time are we at? Oh wow, we got a lot of time. Okay, so we're going to talk about the Wald estimator now. Just recall that this is our equation to start with when we just looked at the OLS. Yi is a function of alpha plus beta Si plus eta I. So we're saying that wage is explained by education and then some error term, whereas the error term eta I, there might be an omitted variable bias problem in it if we have ability contained in that variable in our outcome or our error term. Okay, so we can write our Wald estimator as, this is the same really as the equation we wrote before to explain beta, but this is in the Wald format. So beta is equal to the expected value of yi given zi equals 1 minus the expected value of yi given zi equals 0. So that's the same as just our beta for our reduced form as we talked about earlier, just in expected terms, okay? And so then the denominator is our beta of our first stage regression, which is zi on si. So that leaves us with the expected value of si given zi equals 1 minus the expected value of si given zi equals 0. So this is the exact same thing as what we talked about before when we had the covariance of yizi, covariance of sizi. This is just in terms of expected values, because if you think about it, the treatment effect is just the difference in means, because we're assuming that the zi gives us removes selection bias, so it gives us causality. So we can basically think of it the same as randomization when we have zi, but remember that we only care about the relationship between y and zi in terms of si. So that's why we have this denominator. Otherwise, it's the same as our randomization difference of means, right? So it's super simple, actually. So it's always our reduced form equation. So this is our treatment effect for the reduced form divided by the treatment effect for the first stage. Is that clear? Do you guys remember the difference between reduced form and first stage? I feel like I've talked about it a lot, but if I went by it too fast, certainly let me know. Okay, great. Definitely just look over it before Monday so you don't feel completely confused, and if there's some problem areas, let me know at the beginning of class on Monday. Okay, so heterogeneous treatment effects is just the idea that maybe different people are affected differently. They have different treatment effects. That's what heterogeneous means, just differently. Oh, I have a question on the zi. So what does it really mean when we have zi equals 1 or 0? So you say you have a household, and recall that, I'll go back here. So like we have the difference between our outcome when zi equals 1 and when zi equals 0. Think of it as like a dummy that's either turned on or turned off. So for instance, take our Sesame Street example. Suppose that distance is a dummy variable. So distance, let's say it's like closeness to the tower. So let's say zi equals 1 if you're close enough to the tower to access Sesame Street. So zi equals 1 if you can access Sesame Street based on your distance. And then zi equals 0 if you're too far away. So then you can see how our outcome variable when we're close enough to access Sesame Street minus our outcome, the average outcome when we're too far away to estimate to watch Sesame Street, is basically the diff. That's our first, oh my god, I can't speak. That's our reduced form, because that's basically our two possibilities of our zi. Either you're close enough or you're too far away, and that will give us our treatment group and control group and the two outcomes associated with those two groups. Yeah, the instrument can be continuous as well. So how would that work? I equals 1. I mean, then it's just a continuous. This is just an easy way to put it into the walled. I don't think you can make a walled estimator when you have a continuous zi, but I can double check that. I think it's only for discrete terms. Like if we had a continuous, it would look like it would look like this, right? Then we just have the relationship, the covariance between yi and zi, divided by covariance si zi, because then we have all of our data on both points. But if we do have a discrete zi, we can use the walled. Oh, what is the difference between the walled and the late? I got confused on that. Okay, we haven't talked about the local average treatment effect yet, but that has more to do with inference and how we are understanding our treatment effect. Okay, so we'll talk about that a bit later. But the walled is the estimator, and the local average treatment effect is how we interpret it in terms of external validity. But we'll talk about that more on Monday, hopefully, so don't worry about it too much right now. Any other questions? Okay. Just let me know at any time. Okay, so we're going to talk about heterogeneous treatment effects, and that's when different people are treated differently. They have different treatment effects. So yeah, that's an obvious statement. Remember that we're primarily interested in impact evaluations, hence the course name. Okay, so our standard causal framework will always just be to start that our outcome variable is a function of our treatment dummy. So remember di equals 1 if you're treated, and di equals 0 otherwise. So overall, we're primarily interested in our treatment effect dummy di, but sometimes we might also deal with issues such as imperfect compliance or heterogeneous treatment effects. So in an IV framework, the engine that is driving causal inference is Zi, right? So Zi is where we are able to draw causal inference. But remember, Di is still the variable of interest. We want to know about our treatment effect. We don't care about distance from the tower, besides anything other than that it's making people watch Sesame Street. The same as we don't care about distance to a college for anything other than how education affects our outcome variable wage, right? So Zi is really just a mechanism to find the effect we really care about between our x and our y. So it's really useful to think of our Zi as like the start of a causal chain. So Zi is going to affect our x variable, our treatment dummy di, and that's going to then affect our outcome variable yi. So that's really causal chain of interest, how x and z are related, and then through that, how x affects that y. Ugh, so many letters. Okay, so let d1i be individual i's treatment status when zi equals 1. So d1i, if you are treated by the instrument or your instrument turned on, I don't know how to say it, but when the instrument variable is true, and then let d0i be individual i's treatment status when zi equals 0. So then we observe the treatment status. Di is either, this is just an easy way of saying zi either equals 1 or 0 for you, and that's going to affect whether your di is 1 or 0. And so di is a function of pi 0 plus pi 1i zi plus ei. So di is a function of zi. Okay, so if that's true, then pi 0 is the expected value of d0i. So that's like the average, treatment status for d0i. And pi 1i is the difference between d1i minus d0i. So basically what that says is pi 1i is the heterogeneous causal effect of the instrument variable zi on di. Okay, so it's the difference between D1i and D0i. And so that's just basically saying Zi is somehow determining our treatment status. Kind of a confusing way to say it, but it's just showing that there is a relationship that Zi determines what your treatment status will be in an exogenous or random way. Okay, so this can be true even if there's different basically effects for each different individual. So for example, like I mean, this is kind of confusing, but like the Zi, it can affect your treatment status in different ways depending on the individual. So what we really want is that the instrument is affecting the treatment status in the same way. So that's called monotonicity. And that means that basically we don't want the instrument of choice, so say distance from the tower, to affect some people positively and some people negatively, or push some people into receiving treatment and some people not. So for instance, like if you're closer to the tower, it makes some people watch television, but being closer to the tower makes other people not watch television. If you have opposite treatment of Zi on Di, it's really impossible to interpret. So that's why we need the Zi to affect Di in the same direction for everyone. Okay, so for the heterogeneous case, we need basically the same condition as before, that the instrument is good as randomly assigned, which is just saying that we have the exclusion restriction satisfied. Okay, this is exclusion. So it's as good as randomly assigned means that there's no selection bias. So we talked about randomization is the gold standard methodology because it removes all selection bias by design. And a good IV should have the same exogenous property that when we use this instrument variable, we remove all selection bias. Okay. And that means that I has to be exogenous of potential outcomes yi, and that's saying that no selection bias, obviously, Zi doesn't affect any other variables that also affect y other than x. And so this assumption is essential for causality because without it, we can't say that there's a clear effect of Z on X on Y, because that might also affect a different number of other variables that affects Y. Okay, and then the second assumption, same as before, is relevance, that there's some relationship between our instrument and our treatment dummy. And then our final assumption is monotonicity. That's what I said before. It's that either Zi has a positive effect on Di for everyone, or it has a negative effect for everyone. It can't have a positive effect on whether you receive treatment for some people and a negative for others, because then we just won't be able to estimate an effect. We're going to take a weighted average, and it's just not going to make any sense. So we really do need Zi to affect how you receive treatment in the same direction for everyone. Okay. Is that clear monotonicity or not? Just think about an example in your head and say, okay, so if Zi is true, so let's say distance to tower, so you can be, if Zi equals 1, you're close enough to the tower to watch Sesame Street. If Zi equals 0, you're too far away. So if I'm close enough to the tower to watch Sesame Street, and that makes half the people watch Sesame Street and half the people not watch Sesame Street, but when they're further away they will. I mean, that example is impossible, we know. But if something like that happens, then that's not a good IV because doesn't have monotonicity. So we really need that requirement for estimation to make sense and be causal. Okay, Any questions for me or comments, concerns? Great. Okay, I will let you guys go and we'll pick off where we started. Start where we I can't speak today. We'll start where we stopped on Monday. So I will be working on marking your assignments and hopefully I can get that to you maybe next week, Wednesday. It's just taking me some time because everything's online. So I don't know. Okay. I'll see you guys on Monday.